let's say a few words about the speed of light as an absolute speed limit using our light clock as an example. Remember, we derived our expression for the Lorentz factor gamma in this form, 1 over the square root of 1 minus v squared over c squared. Clearly, there is a problem here if, remember, v is the relative velocity between two reference frames, two inertial reference frames. We've been using Alice and Bob. So if Alice is stationary, she sees Bob perhaps go by in a spaceship at velocity v, according to her lattice of clocks and measurements. And then Bob could be, in his spaceship, could imagine, really, he could be stationary. He could see Alice receding behind him at negative velocity v, according to his lattice of clocks and measuring system. So v is the relative velocity between the two reference frames, c the speed of light, of course. If the relative velocity between two reference frames is c, if Bob is traveling by at the speed of light compared to Alice, and Alice measures Bob at the speed of light, look what happens, of course. We've got c squared on the top, c squared on the bottom. This is 1. 1 minus 1 is 0. Square root of 0 is 0. 1 divided by 0 is infinity. Gamma becomes infinite. So that's a hint right there, a very strong hint, that something either can't go at the speed of light, or we have problems with our theory. And since the theory has been well verified, we say, okay, this must be an absolute speed limit, that nothing can actually get up to the speed of light. You can do further calculations with this that really go a little bit beyond our course in terms of the amount of energy needed to take a massive object, anything with mass, and get up to the speed of light. And you find it essentially infinite energy is required. So there are other arguments, too, for why you can't get there. There are actually, over the last, it's about 30 years or so ago, there's the idea that maybe you can't get to the speed of light, but perhaps there could be things that actually were faster than the speed of light, sort of on the other side, as it were. And they were given the name tachyons. There was some theoretical work done on them, some development to figure out whether this would actually work out. The theory ran into some insurmountable problems along the way eventually, and therefore was discarded. But for our purposes, certainly, the gamma factor, the Lorentz factor, is indicating can't get up to c. You can get close to c, in which case gamma becomes very, very, very large, but you can never quite get to c because then it becomes infinite. Now, let's see how that factors in with our light clock example. Remember, from the light clock, we found that the elapsed time on a moving clock, if I'm observing here, we've got two identical clocks. Maybe Alice is here with me, and we see Bob going by with his light clock, and we compare the two. The light that we see in his clock has to travel a longer distance than the light in our clock, and therefore his clock ticks longer. I should really say ticks slower. Each tick takes a longer time to go from here in this diagonal path versus our just up and down path with our identical light clock. And therefore the elapsed time on a moving clock is less than the elapsed time on our identical stationary clock. So this is us observing Bob's clock going by. Remember, for Bob, his clock, he's just sitting there with his clock. It looks fine to him, and he's viewing our clock as running more slowly than his. And again, it all goes back to the two basic principles that Einstein enunciated, and the fact that simultaneity and clock synchronization is relative. But just to remind ourselves, time dilation. Elapsed time on a moving clock is less than the elapsed time on an identical stationary clock. Here was the formula. So again, delta t, the elapsed time that we'd measure in the lab, is gamma times the elapsed time on the rocket clock. So the number of ticks on the rocket clock, maybe we get 10 ticks on the rocket clock as we see. The number of ticks on our clock, depending on gamma, might be 20 or so if gamma was 2 in that case. The moving clock would run more slowly. Or just to reverse the equation here, the rocket clock, the elapsed time on the rocket clock is going to be less than the elapsed time on the lab clock by the 1 over gamma factor. Well, what if gamma then is infinite? What if we put c in here and make gamma infinite? Look what that indicates with our time dilation equation. Well, first of all, we haven't encountered anything physical reality that is an infinite quantity. And so that's why even the math might say it's infinite. We say, we can't have that physically, but just imagine if we could here, this would say that the elapsed time in the lab equals infinity compared to the rocket clock. That's sort of weird. That how do you have an infinite elapsed time on our lab clock ticking away right here? Get a little more insight perhaps with the second equation that this says the elapsed time of the rocket clock 1 over gamma times the lab clock. So whatever the lab clock is saying, 1 over infinity, if this really is infinity up here, that's just 0. It's saying no matter what the lab clock says here, the rocket clock is 0. In other words, the rocket clock never moves. As the lab clock is ticking away very nicely, we're looking at here, it's ticking away nicely. If Bob was moving by in his rocket with his light clock there, and he was moving actually at the speed of light, we would see his clock as never ticking at all. It'd just sit there. It'd be frozen. Time would be frozen as far as we would see his clock going by according to our lattice of clocks. In other words, we'd see him going by, and our lattice of clocks would be there. We could take flash photographs all the way along our lattice of clocks and look at those photographs later and see what Bob's clock said along the way in each of those cases. And his clock would be the same thing for all of them if he was traveling at sea. His clock would never tick at all, even though ours were all ticking nicely. And we can see that geometrically a little bit with our light clock diagram here. Remember, this is like 3 snapshots of the light clock. Snapshot 1, snapshot 2, snapshot 3. It's moving at velocity v here, and so we had the light beam as we see it in the lab. As Bob goes by, his light beam on his clock would go up and then back down again, bounce off the upper mirror here, and then down to the lower mirror. That'd be 1 tick, while our clock would just be going up and down like that. Well, think about what happens if v equals c. So if we say, we'll just do this even in orange here. So we'll say v equals c. What happens in that case, sort of geometrically here? Well, that means from 1 to 2 here, okay, his light clock is moving with velocity c. In that amount of time, okay, to move, say, this distance here, green, so in that amount of time it's moved that distance there. So, to get to this position too. So if this light beam here is traveling up toward the upper mirror, how far has it moved? Well, it's moved the same distance. So if we sort of spin this up here like that, that's where that light beam would be at that instant. When the light clock gets to position 2, it's moving, we're assuming it's moving at velocity c, speed of light. It's moved to here. The light beam heading up to the upper mirror can only go that far. And so what happens then, when it gets up, presumably to that mirror's not there anymore. Because a little bit later on, it's moved now over here to this position here. So it's right there. And the light beam can't hit the mirror there. In fact, the light beam can never hit the upper mirror, because the upper mirror is always just out of its reach. And in another analysis we'll do later on, we can actually do this more quantitatively to show that in this instance, the light beam will never hit the upper mirror. It will never get there. This, in other words, saying the rocket clock is frozen. The light beam actually, in fact, as you elongate this out, the higher the velocity here is, in terms of this triangle sort of gets elongated out this way. So a very high velocity, the light beam would go way over here and bounce, and then way back down. And when it gets up to C, it never can catch up to that upper mirror. And so it never ticks at all. And it actually becomes just a horizontal line there, never reaches the upper mirror. Rocket clock is frozen. Again, we'd say that's an unphysical situation for a moving object like our light clock here, and therefore we don't expect it to actually happen. But again, the math here gives us some hints that, that's a very strong hint, that that's not possible. And that's backed up just by looking at the situation physically or in a geometrical sense that the light beam heading toward the upper mirror will never be able to reach it, because the mirror is always, because the mirror is moving at velocity c is supposedly this way, it'll always be just out of its reach. So interesting to see how the velocity of light then becomes an absolute speed limit. Later on, we'll also see that there's some cause and effect arguments that also say why this can't be possible. In a previous video clip, we looked at combining velocities, really adding velocities is what we were doing when we had motion in the x direction. So remember, we used Lorentz transformation, and you got an equation like this. And what I've done here is added these x subscripts to the velocities. U sub r, remember, is the velocity in the rocket frame. Our example was Bob here going with some velocity, and Alice is here, so I get her in the picture. Going with some velocity v with respect to Alice's frame of reference, and shot off an escape pod in his direction of motion with velocity u sub r compared to him. And we discovered then the velocity that Alice would observe the escape pod to go followed this equation here. And we did a few examples with that just to check out how it might work. And in particular, we saw that even though the two velocities here, the velocity of Bob with respect to Alice of his spaceship, and then plus the velocity of the escape pod, if they both added up so they were greater than c just by adding them together, this equation would be such that the result would never be greater than c in terms of what Alice observed in terms of the velocity of the pod. What we want to do now is do another case where what happens if Bob shoots it up maybe straight up or just perpendicularly off to the side here, and figure out what would Alice see in that situation. And interestingly enough, this will bring us back to the light clock that we were talking about recently. So here's the situation. Bob shoots it up at some velocity u sub r, and we'll use a subscript y to emphasize this as just in the y direction now. We could say it's the z direction, but we'll choose the y direction for that direction. And of course, definition of velocity, delta y sub r over delta t sub r. This is for Bob now. He says, how far does it go in the y direction, and what's the elapsed time for how far it's going in that direction? That's going to be the definition of the velocity. And so now let's write down a couple of equations actually for u sub ly. That's what we're after here. What does Alice observe the velocity in the y direction to be? So u sub ly here is going to be delta yl over delta TL, just by definition of the velocity. And this is why I, as a reminder, added the y and z components to our Lorentz transformation. Remember, they don't transform at all. They're the same. And so delta y sub L is going to be the same as delta y sub R. So this is going to be delta y sub R over delta t sub L. But that does change, of course, by our equation we used before. Remember, we could use deltas in here to indicate change of quantity. So we'll write that as delta y sub R on the top. And then delta t sub L, remember, is using the equation here, is going to be gamma times delta t sub R plus v over c squared delta x sub R. All right, again, these are the quantities that Bob is measuring. And we're assuming everything is constant velocity here. For those of you who've had some physics, you say, well, what if it's accelerating? Well, we're not dealing with that case here, and therefore we can define velocity as simply change in, not change in direction, but the direction, elapsed direction if you want, the direction covered divided by the elapsed time. So delta y sub r over this quantity here. Again, we'd like to simplify. We'd like to be able to get some of the u sub r rocket frame y components in here. And so let's pull out this delta t sub r, sort of like we did before, and see what happens here. So we have delta y sub r on the top still, and got a gamma here. The gammas don't cancel this time. And we're going to pull out a delta t sub r from that expression. So we've got delta t sub r times 1 plus v over c squared delta x sub r over delta t sub r. Okay, so delta t sub r times 1 is the delta t sub r. Delta t sub r plus this thing gives us that, because the delta t sub r's would cancel there, of course. But then this is a little strange here, because notice that we're doing an equation for the y component, but we've got some x components in here as well. Remember what this was? This is just the velocity of the pod in the x direction in the rocket frame. Okay, so we could write, in fact, just to remind ourselves here, u sub rx equals delta x sub r over delta t sub r by definition. Very good delta there. That's even a worse one. There we go. Okay, now. So But in our example here, note what happens up for Bob. Not what happens, but what is happening for Bob here. There is no velocity of the pod in the x direction. Remember, Bob's stationary as far as he's concerned. He's shooting the pod straight up as far as he's concerned, or straight off to the side. And therefore, there is no velocity in the x direction for this example. So in this example, this equals 0. No velocity of the pod in the x direction as far as Bob is concerned. And so that's nice, because this whole term then here is 0 for us. So this thing here turns into 0 for this case. And look at what we're left with here. Delta y sub r divided by delta t sub r, and also divided by gamma. Delta y sub r divided by delta t sub r, that's the velocity in the y direction for Bob in the rocket frame, u sub ry. So this simply becomes u sub r in the y direction divided by gamma. Okay? Now, we're going to come back to that in a minute, but let's do one other thing here too, just to make sure here, because for Bob it's going just straight up, right? But for Alice, Bob is moving that way. So Alice may, and probably will, and actually will observe that the pod is going to go up at an angle, because you do have the velocity of motion here of the spaceship involved. And so let's see if we can get that in here as well. So we'll squeeze it in right here. We just did that. And what we're going to do here, make a little room. So let's do u sub Lx. In fact, here's a formula we want to use right here. Don't have to rewrite it, because we already wrote it. And so in this case, u sub Rx, remember we just finished talking about, I just erased it, that's 0, right? As far as Bob is concerned, no velocity in the x direction. So I get 0 plus v all over 1 plus, well again, u sub Rx is 0 to Bob in this example. Therefore, this whole thing is 0, so I just get 1 plus 0. And in fact, we did this example when we were talking about the transformation equations here for the velocity. This just gives us v. So there are two components as we talk about the velocity here for Alice. One component is just the velocity v in the x direction, because that's just the motion of the spaceship here. And the other component of the velocity in the y direction for Alice is u sub ry over gamma. So it is whatever velocity Bob sees, they're shooting up, then that's going to be divided by gamma. Note one very interesting thing here. Gamma is in the denominator. So as the velocity of light gets, not velocity of light, as the velocity of the pod shooting up here gets faster and faster, closer to the speed of light, remember what happens to gamma? Gamma gets close to infinity. And therefore, this whole thing, no matter how big this velocity is, this is like something divided by a very, very, very big number. This goes to 0. So this approaches 0 as v approaches c, or gamma, another way to say it, gamma approaches infinity. So that's very interesting, because what that's saying is no matter how fast Bob shoots up his escape pod, if his relative velocity is close to the speed of light, Alice sees almost no upward velocity at all. This is Alice's upward velocity in the y direction that she's observing. If gamma is very large, if Bob's velocity is very close to the speed of light, this whole thing goes to 0. And all she sees is the sideways motion from the x direction v. And the reason, I mentioned the light clock a minute ago, because remember, we did an example with the light clock where, of course, the light clock, so here's Bob's light clock, moving with velocity v in that direction. And of course, we saw from Alice's perspective, the light beam goes up here, and then, well, down there, so the light clock has to get a little farther over there. And we talked about, as v gets closer and closer to the speed of light, remember that, get the green in here again, that this light beam can never catch up to that upward mirror. Because if this gets close to c, then this light beam has to travel too far to the upward mirror, and by the time it essentially gets there, the mirror would be farther away. And in fact, as it gets very, very close to C, this triangle gets very, very elongated. And in fact, this light beam never gets up to that top mirror, and it's frozen. The light clock, as Alice would observe it, if Bob could go by at the speed of light, which he can't, but if he gets very, very close to it, it's almost like the light clock is frozen. It ticks very, very slowly. It's just a time dilation effect. Gamma is very large, and therefore Bob's clock ticks very slow. If you could actually reach the speed of light, it's frozen. And that's what this mathematics here is telling us. Another way that we argued for qualitatively earlier, that I never put the green in here, but if this is the velocity of light, if we're going c here, and so it can get up here at c, but it never gets up to that top mirror, that's what this is telling us. It's saying if we can go at the velocity of light, if Bob could shoot, or if Bob could have a spaceship at the velocity v of light here, then this would be infinite, and Alice's observed velocity for the escape pod going up, no matter what the velocity of the escape pod was, would be 0 in the upper direction, and she'd just see the c factor going across there. So tells us another way. It's good to have these consistency checks here, because you could say, just to make the point in one other way here, this light clock is sort of like the escape pod if the escape pod, instead of being an escape pod, were just a beam of light going up in that direction. Make it squiggly for a beam of light here. A beam of light going up in that direction, c, that's exactly what the light clock is. For Bob's perspective, it's going up and down like that. And so that's like shooting light beam directly perpendicular to Bob. If he's traveling at velocity c, then what this is saying in this case is Alice never sees that light beam go up. She just sees Bob go this way, and the light clock is frozen in that instance. So an interesting confirmation of some of the other things we've done. This is one of those things sometimes it takes a while just to sort of mull it over, think about it, work through it, convince yourself of that it actually makes sense, put in some numbers, try things out, sort of get a feel for what's going on here. Let's now look at the key things we did here in week 5. So do a little summary. Not quite in the order we did them, but hitting all the high points. Clearly, one of the big things of the week was the Lorentz transformation. It was sort of the theme of space-time switches. In other words, switching between one frame of reference to another frame of reference and having some nice equations such that we don't have to start from first principles all the time in doing that. So the idea was, of course, that if you have two frames of reference, A and B, maybe Alice and Bob again, and so if you have, say, Bob doing a measurement in his system, he sees an event as certain x, y, and z space coordinates and a certain time on his lattice of clocks, then can we transform that into the coordinates in Alice's system? And so here were the equations we came up with. Again, we won't go into all the details because we spent some time actually exploring them a little bit to see what the implications were. But for x sub a, and remember A and B here, we're doing B as the frame of reference moving to the right, positive x direction at speed v. So another way we've written these in the past is with A being the lab frame of reference and B being R for rocket, the rocket frame of reference. And sometimes that's easier to visualize and remember which way it goes, as long remember it's the rocket's going to the right for these equations here. You may remember if we have a situation where the rocket is going to the left, then we have minus v and minus v over c squared in those cases. So again, advice is memorize the basic situation, make sure you understand which direction it's going, and what's the rocket frame, what's the lab frame, or what's the rest frame, what's the moving frame, or here we're just doing A and B for the rest frame and the moving frame in this case. So this would be Alice watching Bob moving, and he sees an event with certain coordinates that involve xb and tb, and therefore Alice's coordinate where that event occurs, x sub a, is given by this. T sub a on her clocks is given by this. Remember the y and z directions, we often don't deal with those, but if we had to, they are not transformed. There's no difference in them because the things like the length contraction effects, time dilation effects, only apply in the direction of motion. So we don't have to worry about those typically, at least in terms of the more complicated transformation equations. So we explored those equations a little bit, and then we used them to revisit the idea of leading clocks lag. And we found that the quantitative amount by which they lag is dv over c squared, where v again is the velocity between the two frames of reference. D is the distance between the two clocks in the frame that's moving. So again, if you have a rocket ship with two clocks, one at either end, and we see it moving past us, then the leading clock is going to lag, as we've argued qualitatively before this week. The leading clock will lag the trailing clock as we watch it go by. And now we've discovered the exact amount it will lag by. And this distance d is the distance in the frame of reference, in this case, of the spaceship. So it's not a contracted length or anything like that. We'd set the spaceship down, measure the distance between the clocks at rest in that frame of reference, say it's d, and then as it was moving past us, the lag time between the two clocks would be d times the velocity of between the frames of reference and divided by c squared. And note that in general this is a very, very small number, and that's why we don't see it in our ordinary everyday experience. Even with velocities up near the speed of light, 0.9 c here, we still have this c squared down here. So this does not get significant until both d and v are fairly large, and then we start seeing that effect. But what was nice about it, and why one of the reasons we did it here, was that it helped solve our Star Tours puzzle, where we explored length contraction, time dilation a little bit more with Alice and Bob. Bob taking a trip to a nearby star, and we looked at it from Alice's perspective and Bob's perspective, and the different things they would see on their clocks and what lengths they would measure from Earth to the star, or the star moving toward Bob, and so on and so forth. And we hit sort of a wall, a puzzle there, and discovered that it was answered very nicely by remembering this leading clock's lag concept, which really is a special case of the whole idea of the relativity of simultaneity, that clocks in one frame of reference will be synchronized. Say Bob's clocks in Alice's frame of reference will be synchronized, yet if one looks at the other's clocks, they're not synchronized. And they're not synchronized by this factor between any two given clocks as you observe them. And that all goes back to, remember, Einstein's principle that he derived from his two postulates of the constancy of the speed of light. The speed of light is the same to all observers, and that's where we got these relativity of simultaneity effects, as well as the time dilation and length contraction effects. So, leading clock's lag we discovered by this amount d, v over c squared there. And then another thing we looked at was combining velocities. We'd done this before in our Galilean transformation case, or our everyday experience case, if you have a car moving along and you shoot a basketball out from that car at a certain velocity, with respect to the car, the velocities just add if you have an observer observing what the velocity of the ball is, or it's just like running forward and throwing something versus just throwing something. Well, because the speed of light is an ultimate speed limit, which we also talked about this week, then you can't have things, if you have something going at 0.9 c and you try to add something at 0.7 c. So if you have Bob in a spaceship going at 0.9 c by Alice, and then he shoots out an escape pod going at 0.7 c, or whatever it is, with respect to him, Alice does not see it as 0.9 plus 0.7 c, 1.6 c. It will never be faster. She will never observe it faster, the escape pod going faster in her frame of reference than the speed of light. It will always be less than the speed of light. And so another thing we were able to do using Lorentz transformation is derive a formula for figuring out exactly what Alice would see in that case. And I've used it in the form A and B here again, but Alice could be the lab frame, B is the rocket frame for Bob, and so so you see UB is the velocity of the object is measured in the moving frame. So again, imagine the escape pod shooting out from Bob's spaceship, and if it's going at U sub B with respect to Bob in his spaceship traveling away from him, then Alice will measure it using this formula, the speed. So it's UB, U sub B, plus the velocity between them. And that would be normally the Galilean transformation in terms of just adding velocities, the normal addition of velocities. But we've got this factor on the bottom. And again, note that unless U sub B and V are close to the speed of light, this thing is typically very small, and therefore we don't see that effect. But at high velocities, we will see this effect. And we demonstrate also that no matter what U sub B is and what V is, if they're both 0.9 C, for example, then even so, U sub A will still be less than the speed of light. So we did some examples like that. And we talked about the ultimate speed limit in terms of just what happens to gamma. If you could actually have an object like a light clock moving at the speed of light, gamma becomes infinite then, which is clearly a problem. So it's an indication something is going wrong there. And we also looked at this idea of time freezing if you could move at the speed of light using our light clock example. That time seems to slow down, but we have to be very careful how we talk about this, because in many cases when you hear people talking about the special theory of relativity in Einstein, they say, well, right, evidently the physicists tell us when things move very close to the speed of light, time freezes. Remember, it's not, if we could actually travel in a spaceship with our light clock near the speed of light, 0.999 C, say, so a very large gamma factor, we'd see nothing out of the ordinary inside our spaceship, that is. Just our light clock would be functioning very, very nicely, ticking away normally. It'd be a person outside our spaceship observing our clock as it goes by that would see a really strong time dilation effect, such that we can never reach C, so time would never freeze. But if we could reach C, remember we did an example with combining perpendicular velocities and a more qualitative example with our light clock here, just to show that if we're actually moving at the speed of light, the light beam heading up to the upper mirror of the light clock would never get there, because the mirror would always be out of reach if the light clock would move at speed C. So, brief summary of especially some of the key equations we looked at this week and derived this week and used this week, and the concepts behind them.